unmute myself. Smart. Yeah. Yeah. Did you guys leave before you could see it? Oh, I'll just kill myself. That's fine. Mhm. Mhm. Yeah, out, in, except for the these ones. You're queen, right? Ready. Okay. Yeah. Yeah. Oh. That's long anyway. I'm sure. Okay, why I did that. No one remembers why I still. I still. I don't know how I did that. We did. That's what's happening to you. What else? I don't think I got my chickens last week. Was it? I don't remember. I think I got this class late. And some people getting them. I don't think I did.
These are the only ones that there's a couple that I haven't graded because the work wasn't turned in, but I think I've seen a lot of your work, right?
Yeah. Let me check my back.
Okay.
Right.
How's everyone doing? Good. Oh, that switched real quick. Yeah. Oh. Good. Yeah. All right. Okay. So less respondents than normal. Bad. Not bad. All right. Anyone get to see the comment yesterday? Okay. I may regret saying this, but do we want to have an event tonight just for this class?
What time?
It would probably start at 7. I'll get the telescopes out just for this class. I need a show of hands because I won't do it for less than 10 people. You're actually going to show up though. Because if I show up there and I'm alone, I'm going to be real sad. 1, 2, 3, 4, 5, 6, 7. Yeah.
You go into my lab and pull it out.
At 7?
Oh, no, I do. Wait, no. That, no, that's it. Yeah,
Which lab is it?
the lab for this class.
For this class?
Yeah.
Oh, interesting.
Yeah, tell me.
Who is it?
Well,
Hey.
so what?
If O'Reilly's got a whole lab prepared for you, that feels rude. You think I should still do it?
Invite him too.
Okay, this is a very good point. I'll go find Riley after this. If lab's canceled, he'll send you an email and we'll go look at the comment instead. Relax. If. Big if at the beginning. Okay. What's this? Clouds. Good. This is a photo from one of your classmates. Came in today, wanted to know about clouds. We're going to be talking about atmospheres. And I told her that you can go to Cloud Appreciation Society. It's one of my favorite places because I fucking love clouds. There's a whole highlight on my Instagram, which is just me explaining what clouds are to my friends. And so we're going to look at a lot of clouds, but generally speaking, we won't go into like the details of how the clouds form unless you are really interested. So we'll talk more about like global conditions for atmospheres. But if you've ever thought to yourself, man, that's a weird cloud, I wonder how it formed, or like what is lightning and why does that happen? You just tell me towards the end of the atmosphere section and we'll just add a little bit more. That seem reasonable? And if already talking about this much clouds is too much, that's fine. Essentially what's happening here, this is a form of cirrus clouds. These are really high up. And then these water vapor, they make it high into the atmosphere where it's cold, and then they become clouds. But there are layers in the atmosphere, and one of them is moving faster than the other. So it drags the cloud along, and as it drags it, it sucks it up a little bit to form these little uplifts, look like little canes. So usually when you look at clouds, they're telling you something very specific about something you can't see, which is the air all around you. You know, sometimes you see like leaves moving around. Well, this is clouds telling you about the atmosphere itself. Cool, right? Okay. We're also going to talk about this weird thing. Why is it red down here and blue up here? That's strange. We're going to talk about planetary atmospheres as a whole. And we're going to think about them. We're going to talk about them in various contexts. We'll talk to them first about like how do atmospheres work? What is the thing that makes an atmosphere what it is? And then we'll talk about them at the individual planets and how they're different, how they're composed of different materials. And then we'll talk about them in the context of the giant planets. So we'll talk about Jupiter, Saturn, Uranus, and Neptune, all of which don't have surfaces. It's just gas all the way down. At some point, we'll talk about climate change. because that's inevitable. Not the climate change, but talking about it is, sorry. And then we'll talk, this one is the one I just told you about. Why is the sky blue? So you'll be able to say, what? Why is the sky blue? I think everyone's favorite question, right? Is it reflection from the ocean? Raise your hand for reflection from the ocean. Raise your hand for witchcraft. That's pretty close, pretty close. Okay. All right. And you've all been reading, right? You really enjoy reading the book? Okay. All right. Let's prove that. Which of the following is the lowest layer in the atmosphere? Okay, we have some different words here, which you've seen because you've all been reading. But one thing that we're doing is we're thinking about the atmosphere. So let's break apart the word atmosphere. Sphere means sphere. We've all got that. We saw lithosphere. That was like the rocky sphere, the outer part of the planet. Well, there's a layer above it, and that's the atmosphere. Okay. So which ones of these is the lowest layer of the atmosphere? Click in here. All right, is that it? 3, 2, 1. Okay, so for the 3 folks who picked lithosphere, are you just saying that because like I said that? Said like the rocky layer? Because the atmosphere starts when it's fluid, when it's gas. Okay, so the rocky layer is not it. And then you all read, so you know which one it is, right? Yeah, you know which one it is. Exosphere is at the top. Thermosphere is warmed by the ultraviolet. That's above. Planes fly in the stratosphere, and we're living in the troposphere. See how I staggered them so you wouldn't be able to tell? Okay. All right. These are the planets. Those rocky planets that we know and love. Which of them have atmospheres? Can you tell from this picture? Yes, everyone can tell from this picture. Does Mercury have an atmosphere in this picture? No. Does Venus have an atmosphere in this picture? Yes. Yeah. Does Earth have an atmosphere in this picture? Yeah. How could you tell if you couldn't breathe here and live here? What about this picture tells you there's an atmosphere? Yeah. Yeah, slight blue ring out here. That's from the effect of like looking through the atmosphere, so it gets enhanced. Yeah, yeah, spirally clouds. I love spirally clouds. That's like what I study professionally. Spirally clouds on this body. Oops, I gave it away. But okay, well, damn it. All right, moon. Does the moon have an atmosphere? No. Does Mars have an atmosphere? A little. Yeah, it doesn't look like it there though, right? Kind of a boring Mars. So we should update that photo because mine. All right. All right, don't write this down. This is just for your information. You can find this in any book. You can find this in any table. It's pretty straightforward. Okay. So Mercury and the moon, they're rocky. And they have basically an exosphere. So anything that is created on the surface, let's say there's a piece of ice on the surface and it gets enough energy to evaporate or sublimate, that water just immediately leaves. Doesn't stick around and contribute to anything that you could use like harvest as an atmosphere. It just leaves. So it's called an atmosphere. So it's like rock vapor stuff that's trapped inside the rock, and then it flies off. So technically there's a really small amount of pressure there. And the unit of pressure, because we are very earth-based, like being humans, we all take it as reference to this thing called a bar. Okay, this is not where we go after class. This is the pressure at Earth while you live on Earth at sea level. Okay, if you go up, pressure goes down. If you go down, pressure goes up. Okay, and we'll talk about why that is when we think about pressure in the first place. At Venus, it's mostly CO2, 96% CO2. Humans can't breathe that, so you die if you land on Venus. And that's before you get crushed by 90 bars and 700 degrees. Okay. At Earth, you're mostly breathing in nitrogen. Every breath in is not oxygen. It's mostly nitrogen by a lot. And then you use the O2. So that's why people care about that. You don't use the nitrogen. You can nitrogen fix your plant. And we have one bar. Good. Easy to understand, right? So higher pressure, lower pressure by a lot. Higher pressure by quite a bit. Right? And down here, lower pressure. This is Mars. Interestingly enough, both of these compositions quite similar. So Mars and Venus have very, very CO2 rich atmospheres, and the Earth does not. And so you might be asking yourself, yeah,
Would Mars be good for plants?
Mars would be great for plants. Yeah. Yeah. So Mars would be great for plants, except for one thing. What's wrong with it? Well, not only the temperature, so it's definitely cold, but what's the other thing on this graph? Also bad for plants, yeah. What else on this graph? The pressure. Yeah, so there is an atmosphere, but it's really, really thin. And if you're going to breathe from the air, you need to be able to grab that, right? So the way that we think about pressure, something that we'll talk about in this class, is like all of you are in this room. You're all kind of far away from one another. But if you were in a crowd, let's say you were in a much smaller confined area, you'd be bumping into each other, right? That would be considered higher pressure, right? Because you're bumping into each other more, as opposed to if we all go out onto like that area out there where there's grass and you're like taking pictures of a squirrel or something, you're far enough away from one another, right? I saw that. It's funny. It's like a crowd looking at a squirrel. I was like, that's cute. All right. Here's the big picture. Mars and Venus are mostly CO2, very little N2, nitrogen. Okay. Venus has a big pressure, Mars has a small pressure. Venus is too hot, Mars is too cold. Is it frustrating that I put these colors in the opposite of the way that we just talked about? Or no one noticed? Okay. Earth is weird. Earth is the odd one out. Okay. Have you ever heard of this story, Goldilocks? Familiar with this idea? So you're too hot for the porridge, too cold for the porridge, and then one is just right. So we happen to be in just the right place for life to exist. Not surprising because we're all here. We can't exactly build a theory about why planets form in that way. So we'll need to use more information in order to understand why life can sustain on Earth. Okay. And we need to understand how they're created, how our atmosphere is created, and how do they change over the course of 4.5 billion years. Okay. All right. So why shouldn't atmospheres matter? Why should they not matter? This is a planetary science class. We've been talking about giant planets the whole time. Why do we not care about planets? Rocks are hot inside, yeah, sure. Atmospheres are on the outside. What about their size? Are the atmospheres of the terrestrial planets large compared to their size? No. So I always like to make this analogy. Take a basketball, you place a sheet of paper on the top, right? That's the size of the entire atmosphere. So the mass of the atmosphere is almost nothing. So if you're just looking at mass, you're like, who cares, right? They only go a little farther out. They don't make the planet much larger. Basically the size of the entire planet. And each of the atoms in the atmosphere weighs less than the atoms in the rocks. So for example, rocks are made of stuff like magnesium and iron, and the atmosphere is made up of oxygen. And that handy dandy tool over there tells us that one of those is heavier than the others, right? Okay, so why do we care about atmospheres? Yeah, important for breathing. Anything else? Yeah. Erosion and climate, so they can resurface the planet. Some cases, like asking people in the South right now if they appreciate the atmosphere, I think maybe less than usual, right? There's erosion processes happening that are ruining entire areas. Yeah.
Protects us
From what?
from like UV rays and any like near reference.
Yeah. So you can burn up small asteroids, those become shooting stars or meteors. And ultraviolet light mostly gets stopped, but we don't cook. If you stand out there too long, you're gonna turn red sometimes, right? Anything else?
They tell us about other planets.
Tell us about other planets. Yeah, we can make some comparisons too. Anything else? Yep. They're great for trapping heat. This is really important, right? So if it's too cold, everyone dies, right? Have you ever looked on a map at where England is and then compared it to those same latitudes in the United States? Okay, maybe I'll do this at the beginning of next class. You just draw a line from where England is and you draw it over to the United States, it's like above Canada. That's weird. So if you look, for example, at France, you think, oh, it's pretty nice weather there. They grow grapes and stuff. They have nice wine. And you draw that over, you'd expect it to be like California weather, right? It's much higher. That's weird. Why is Europe so north and yet it's like pretty temperate, pretty nice climate during the winter? That's something that we're going to try and understand with the use of an atmosphere. Okay. These are some effects. So it makes it warmer. That's great. It also redistributes that heat. So if I start by heating the center of the planet, I can smear it around, make everyone warm. It scatters and absorbs light. We said that it absorbs the UV radiation from the sun. And it makes the daytime sky bright that you can see. That's pretty nice. Instead of just having like one stick up in the sky that's shining down a beam, right? We talked about erosion and we talked about the ability to drink water. All good things. Okay. You know where Crestline is? Okay, you drive up to Crestline. Are you at more than 1 bar, less than 1 bar, or at 1 bar? Good? Okay, 3, 2, 1. Interesting. What's a bar again? The place that we're going.
So pressure.
Pressure, the unit of pressure. So what am I asking here? I'm asking if the amount of pressure at the top of a mountain is more, less, or equal to what we feel right now. Is it the same? We have pretty equal answers here. One group likes one of these answers more than the other, but only slightly. Anyone want to defend A? More than 1 bar? Anyone want to defend C? Anyone want to defend B? Anyone who hasn't spoken yet? Yeah, so as we head up, the pressure goes down. So that's kind of weird. Let's think about why we have pressure in the first place. Okay. So pressure is how much of the individual molecules in the gas are bouncing against other molecules. So here I have this wonderful, very scientific diagram of molecules as billiard balls, and they're all bouncing off each other. Okay? And so I put them inside of this perfect red balloon, and on the outside, the number of hits on the surface of the balloon is equal to the number of hits on the inside of the balloon. And then the balloon's walls do not expand or contract. So if there are equal number of bounces on the outside as the inside, the balloon stays the same size. If there's more bounces on the inside, what happens? Presses out, right? Imagine if you had a door and you have people on one side of the door hitting it, and an equal number of people on the other side of the door hitting it, the door wouldn't move. But if the people on one side are greater than the other, then the door moves, right? Okay, that's the idea of pressure. Okay. Which ways can we increase the pressure? Can we heat up the balloon? Can we put more gas in the balloon? Oh, sorry, which ways do not increase the pressure? Sorry. Heat up the gas, put in more gas, shrink the size of the balloon without changing the amount of gas inside, take the balloon up to a higher altitude, or all of the above increase the pressure. Okay. Anyone else want to click in? Okay, so yeah, turn to a neighbor, ask them what they think is going on here. Find someone who doesn't agree with you, even if that means like asking a row in front of you or a row behind you. Because if they agree, then you're not teaching anyone, you're not learning it. Okay. Okay, I just asked Riley. We'll find out. What do we think? Let's revote. You got it? 100%? You ready to explain it?
Oh, that's true.
Everyone wanted to vote. Yes, no, maybe so. Okay, we're just split between two answers. There's one camp that says taking the balloon up to a higher altitude is the right answer, but that will not increase the pressure in the balloon. And another says all of the above will not increase the pressure. Okay, so let's use our analogy again of folks in a room. Okay, the first one's a little weird. Heating up the gas in a balloon, that's not really helpful if you're thinking about people, but heat is how fast they are moving. So if you're thinking about the gas particles, whether they're atoms or molecules, the speed at which they're moving is the way we think about heat. So if they're moving more rapidly, then they would bounce off the walls with more force and thus create more pressure on the other side of that door, right? Yeah.
The hotter a room gets, more people want to get out.
There you go. That is a great analogy. You're right. I'm so good at my job. Okay. So taking the room up to a higher altitude, maybe a little sketch there. We'll think that one through. Okay, putting more gas in the balloon, that's more people. Now they're getting uncomfortable, they're bumping into each other, they're pressing the door more. Okay, that does increase the pressure as well. Shrinking the size of the balloon, shrinking the size of the room. Now they're uncomfortable again, right? They're boxing out. It's really uncomfortable. They want to get out. Pressure goes up. So the first three, we all agree. Okay, it's just the last. So now as I go to the top of a mountain, the pressure around me has gone down. Does that affect the balloon inside? Why?
I don't know why the science, but I know.
So
Take a bag of chips.
yes, yeah, okay, good.
Plates. So like.
It inflates and sometimes you take it on the plane, right? What does it do? It pops. So it's the act of popping that brings the pressure down. The reason it pops is because the pressure stayed the same. It was pushing on that door until the door gave way. Taking it to high altitude on its own does not do anything, right? It's not until you have some people either leave the room, like poke a hole in the bag to equalize the pressure, or you cool the balloon down, right? Everyone chills out in the room and maybe take their seats or like, I don't know, stack on top of each other in a weird way. So if you cool the balloon as you take it to high altitude, the pressure will go down. But just dragging it up there really quickly on a plane, nothing happens, right?
So it's like if two people were like pushing against to like this end, other person went psych, the other person hit their face on the floor.
Yeah, if you remove the pressure on one side, right, you can get catastrophic things. So this is like what happens in a volcanic explosion. You have pressure holding down the gas, and then you make a hole, and all the gas comes out. Okay, so let me show you that. Okay, here's the balloon. You can add more gas. Okay, same temperature. And the pressure goes up inside the balloon. That's the process of blowing up a balloon. When you blow in a balloon, you don't make it warmer. You just add gas and then the walls move, right? Okay, or you can do this. Not recommended, very close. but you could do this. If you get too close, you're just gonna melt it and then it'll pop. If you do it right above, you can heat up the balloon and it'll grow. Okay, this is when all of the bouncing of the molecules, right, becomes more energetic than the outside. And it's gonna expand. Pressure inside is greater than the pressure outside. Okay. Okay, so now we're going to use this idea of pressure to think about the original question, which is, does the pressure go up or down as I go up a mountain? And why? So as I climb to the top of the mountain, what is the cause of the pressure on me now versus when I get to the top of the mountain? Yeah, gravity is pulling me to the center of the earth like this, right? Good. But is that the reason why I feel pressure? So the gas is the thing that's pushing on me. When I breathe in, I'm breathing in a gas that's under pressure. And the pressure is supplied by how much gas is above it. So if I go to the very top of the atmosphere where there's no air, there's going to be no pressure. As I go farther down, it's the weight of all of the gas that's above me that presses down on me. Okay? Similarly, if I go swimming and I go down, I dive down, it's the weight of all of the water above me that would crush me. Right? So like, let's say I was going in some submersible and I was going with my best friend and I built it myself and I go down. It crushes you if you go down too far. That's pressure, right? The pressure is the result of all of the water that's quite heavy above you. Thankfully, air is not as heavy as water, but it is heavy. In fact, on your body right now, you take your thumb, which is like an inch, and you create a square. Now I have several on my palm. How many pounds of weight do you think happen on that inch just due to air? How easy I can move my hand, right? How many pounds am I going through? It's about 14 pounds just on that part of my. So if I look at my whole hand, it's gotta be like 70 pounds, right? Hey, oh, look at that. Do I get stronger just by doing that? No, because it's balanced on the other side by pressure that's pushing my hand up with the same amount of force. So there's force on this side from the weight above, and there's pressure below from the weight underneath. Yeah. Okay. Does that make sense? Okay. So we actually are in a giant fluid that has a lot of weight to it. We've of course become accustomed to being in that fluid, grew up in it, right? But if you jump into the water, you can tell right away this idea of changing pressures. So as you go up to the top of the mountain, there's less material, right? And so the pressure goes down. Cool. Go ahead.
Because then when you go up, it's harder to breathe because the altitude is much higher.
Yeah.
It's at sea level.
It's not the altitude that is important though, it's the amount of oxygen because of the amount of air, right? The air is less. There's fewer air particles. We breathe the oxygen, but what's the dominant part of our atmosphere? Nitrogen. And both of them, you're getting less of. Okay. So this is what it looks like. Imagine you take, Princess and the Pea story. So this is us, the little pea at the very bottom, and you stack up the pillows, right? You stack up more and more pillows, it pushes down on the pillows at the bottom. Right? And the pillows at the top, they retain their shape. They're nice and fluffy. Pillows at the bottom are all squished. Okay? We live at the bottom where the pillows are the most squished. That make sense? Okay. Yeah, it's the basic picture. I don't know how to make it any simpler. Okay. So let's talk about the surface temperatures of the planets. So we're going to connect this idea of the atmosphere that we live in to the light that we talked about last week. They are not different concepts. We need the light to understand the structure of an atmosphere. How does it work? Okay. So everything that you see, every source of energy on Earth comes from the sun, more or less. And on a day-to-day basis, a lot of it's coming from the light from the sun. So let's think about this for a second. Just remember us good. Hold on, let me reset this. Okay. The sun mostly gives off what type of light? The Earth reflects some, absorbs some, and then re-emits what type? And of course, if you've looked at the homework, I apologize because it was cropped improperly. So it looked like 2 questions, but now it's just 1 question with 1 picture. So look at it again if you downloaded it earlier. Okay. Okay, interesting. Interesting. Only 8 of you have it right. So I don't really want you to talk to a partner because they're going to convince you of an incorrect thing. A lot of folks, I think, are picking ultraviolet. And they may be thinking about this picture like this, right? And thinking about ultraviolets on the left-hand side. And so there's this big triangle to the left of the visible. But we see in what part of the spectrum? The visible. Why would we have adapted not to see the most dominant form of light that the sun gives off? Right? So in fact, that's exactly what all of nature has done. It has evolved eyes that use the most information that it can get. And the sun gives off mostly visible light. It absorbs, the Earth absorbs some, right? That's what gives it the color that it has. And it reflects some. So we saw those really pretty clouds. Those are really great sources of reflection. The snow is a great source of reflection, right? And then the question is, what kind of light does it re-emit? Remember that re-emission or emission is the idea of giving off light, right? The light that it generates. Someone has a problem. Say that again. So I'll just wait. What type of light is emitted by the Earth? Someone who hasn't talked yet. You can answer questions. Yeah, go ahead. Would it be visible? Is that the question? Visible? So if the Earth gave off visible light, that would mean that we could see it at night, right? Because night is the absence of daylight. So right now, when you go outside, you look out, you see that the sun is reflecting off of the surface, bouncing into our eyes, where we absorb the light with our eyeballs, right? At night, we can't do that. So it can't be visible light. It has to, the sun gives off visible light, right? But it can't possibly, the Earth can't possibly emit visible light. Yeah. Why is it infrared? Right. Yeah, so if we were snakes, we could all see each other with the lights off. Because we're all warm, warmer at least than these things are, right? And so the earth is warm too. You know, it gets heated during the day, surface is nice and warm, it's warm underneath, that percolates to the top, and then it emits infrared radiation. If it emitted ultraviolet radiation, we'd be in a lot of trouble, right? That would be like cancer from below. We don't have that problem. Okay. So just to reiterate, this is what it looks like. There's the sun. Most of the light comes right here. Narrow band that we used to see. Okay. Okay. And the reason why this is really important, I mean, so you may think to yourself, okay, this triangle is clearly bigger than this little bar, Prismani. Like, what are you talking about? But the thing I want to remind you of that this is a log scale. So this up here is 10 to the 6 or 1,000,000. And as soon as I go down here, that's 10 to the 4 or 1,000. What that means is that it looks like, and then it goes right back down. Okay. That's a detail you don't have to memorize. But just trust me, most of the light is in the visible. That's why we see in the visible. Okay. All right, so here's what the Earth looks like, or a planet looks like, when we think about the process of light. Here, yellow is going to represent visible light. Okay, visible light coming from the sun gets absorbed, heats up the surface, and then the planet rotates. And the only source of light, either coming or going, is the emission of infrared light. So this object you can see at night because it is glowing in the infrared. So if you use like a heat camera, you like see stuff at night, and I'm going to claim that you can see planets at night. Oh, see planets. That's not what I meant. All right. So here's the idea. Here's Saturn. This is 2 images put on top of each other. So here, in the illuminated parts, that's reflected light on Saturn. And here, where it's shadowed, so this here is the shadow of the ring. So the ring is right here, and the shadow is over here. And then this is the night side, the side that the planet is not showing to the sun. And it's shining in the infrared. So here they colored, or I guess I should show here. Here they colored the storms red. They took 2 images, and they put it on our screen for us, really nice. And some of the really cool features you can see in here, of course, is some places are really bright and some are dark. When we talk about storms on the gas giants, the storms permit heat to escape in some places, and then in other places, the stuff falls back down. You know, hot rise, cold sink. That's what's happening. So this is hot material from the interior coming up and then radiating. Does this make sense or no? Okay. Am I going too fast? Fast? Slow? Medium? Don't ask me a question. Okay. All right. So let's talk about the structure of a planet's atmosphere. And this really is like where the entire crux of this part of the class comes in. Okay. So if you can understand the following 2 slides, you got atmospheres. Okay. All right. Up, down is color. Here's visible. Let's start here. Which direction is more blue? With fingers. Up or down? Okay, lots of ups. Good. So ultraviolet, more blue than visible. X-ray, more blue than ultraviolet. And remember that energy goes up with bluer colors, right? So X-rays are much more dangerous than visible light, thankfully, right? Visible light was just as dangerous, but I'll be dead. Okay. And similarly, infrared is more red than visible and therefore has less energy, right? Okay, so let's see what effect that has on atoms. Over here, you have some little molecule, let's say N2. That's the primary constituent in our atmosphere, nitrogen. And an X-ray comes in and it breaks it up. It turns it into two nitrogens, and sometimes it strips off an electron. So the original atom is just obliterated, right? Not having a good day. Okay. If you're ultraviolet light, you can take something like water. See how it looks like the Mickey Mouse upside down? That's like traditional water representation. And it pulls off the hydrogen, rips it off. And now the hydrogen goes on its way, just lives its own life. Never to be friends with that water molecule again. Okay. Visible light is weird. Kind of just at the right wavelength that it can do some funny stuff. So the red goes straight through, and the blue likes to bend. Bounces off of it and grazes off of it. Okay. Really easy at transmitting most light. Visible light. Basically unchanged. Whereas infrared and microwaves, remember what we said about water? Energizes the water. And so you start with a normal Mickey Mouse and then he's spinning. Okay. So this is a source of heat. You have water vapor and you apply infrared, it gets hot. That make sense? Any of these steps not make sense? High energy, medium energy, normal energy, low energy. These unobstructed by the atmosphere. This is absorbed by the atmosphere and destroys the atom or molecule. Here, it strips it, takes a little bit off. Here, makes it warm. Here, does nothing but maybe bend blue a little bit. Yeah.
Would that then have to do with our sky?
Oh, come on, you can't get ahead of me like that. This is like pointed it out a bunch of times. Okay, so we're almost there. So now we can understand this. Okay, so this is the structure of the atmosphere. And it has all those funny words I said earlier. So at the very bottom, this is the troposphere. This is where we live. And this is altitude going up. So it stays pretty like 10, 20, 30, 40, 50. And then I pull a switcheroo on you and I put this little like cut. And then you go up to 500. Okay, so that's the top of the atmosphere. Satellites do not fly in the atmosphere. They're above it. Because if they were in the atmosphere, they would burn up. Not good for the satellite. So above the top of the atmosphere, that's where stuff is flying. And you have all of this light coming in from the sun. Great time. Okay. And all the light comes in and the X-ray starts like slamming into the atmosphere and breaking it apart. And it gets fully absorbed. None of the X-ray makes it down to the surface. It just tears up the top of the atmosphere and the temperatures go way up. Really, really hot. Because all of the energy that was coming down in the form of X-ray, remember we said that X-rays have the most energy, that gets converted into heating up the atmosphere and breaking apart all of the molecules up there. Okay, now you go down a little bit more, and the ultraviolet starts breaking apart water. It only wants to break apart water. Have you heard about the ozone layer? Okay, you know there's a hole in the ozone layer that's being repaired in the famous Smash Mouth song. Know this one? Gosh, you're too young. All right, whatever, it's fine. I'll only feel that for the rest of my life. This part here is a layer in the atmosphere where water gets broken apart and creates ozone, or ozone gets broken apart and creates O2, which would be molecular oxygen and one more. Okay. So this is getting absorbed here. This is the ultraviolet radiation getting stopped by the ozone layer. Great. That means that we don't get too sunburned. If you get rid of it, all of that makes it to the surface and we get way hotter and life gets way harder to live. You're much more likely to get skin cancer, right? Okay, visible, no problem. Makes it all the way through the atmosphere. Very little changes. We'll talk about some of the changes here. And then it gets absorbed by the surface, like we said before. Some of it gets reflected. Sure, at any port here, I could put a cloud and I could bounce that stuff right back up. But for the most part, you absorb at the surface. Surface gets hot, and then you create infrared light. But infrared light really likes warming up water. And there's lots of water right at the surface. So that infrared light doesn't go very far. It gets reabsorbed and emitted and reabsorbed and emitted, and it just bounces around at the bottom, keeping us nice and warm, nice and comfortable. Okay. So if you had a nice day, thank the infrared. Okay. It's nice and warm outside. It's infrared heat from below, not the light from above. Does that make sense? I mean, if you stand out, yeah, obviously you're going to get it. You're just like walking around in the shade. The reason that it's warm is the infrared. Does it make sense? Yeah.
So is it hot in space then?
No. There is nothing in space for it to be hot.
There's nothing in space for the X-rays to break.
Yeah. So for example, if you're in space and you have a nice bag of gas, and let's say you're inside that bag of gas, like a spacecraft, and light gets in, right? Then the gas will get hot very quickly. Right? You need to cool it. That's why all spacecraft have radiators. You get that off of space. Make sense? And if you live in space, like for a year or two, you have, like, you're an astronaut, not just a random person. You have a maximum amount of time that you can spend in space because you don't have any of the protective qualities of the atmosphere. And so your risk for cancers of all types, bone cancer, skin cancers, etc., they go up the longer you spend in space. Make sense?
It's not limited to varied person with
I think it can limit based on your background. So if you've already like worked in a nuclear reactor, you're not allowed to go out that much. But if you're just like brand new astronaut, I think you're fine. Questions? Okay, so let's talk about the layering. Troposphere is at the bottom. Lowest part of the atmosphere. The temperature gets colder. The warmest at the bottom. And it's warmed by the infrared, and you have these convective cells that when the hot rises, and then it rises to a point where it gets, basically there's no ability for heat to be transported anymore. This is where all your weather occurs. This is Mount Everest down here for scale. This is the best part of the atmosphere everyone lives in, right? Planes are right there. Sorry that I covered it up. They fly right at the boundary between the troposphere and the stratosphere. Here's the stratosphere. On Earth, it has this really cool thermal inversion. So it started off by being cold, it got hotter, and then it gets cold again. The only reason that this exists is because of this. If you get rid of the ultraviolet, you get rid of the thermal inversion. Okay. So this is ultraviolet sunlight being absorbed by ozone right at this level. As you move up, the pressure is going down. There's less molecules around. There's less air to do the absorbing. Right? If you got rid of all of the ozone, what happens to the planet? When we know we get skin cancer, what happens to the surface of the planet? Hotter or colder? Hotter, because you have more light that makes it to the surface. Up here, ozone's doing the job of heating up. And I will ask you this homework question, so you should understand this. So you have questions right now, ask them. So if you remove the ozone here, the temperature will go down, and the temperature here will go up. Because the light makes it all the way down to the bottom, unbroken, gets absorbed by the surface. And then you heat up the surface. Okay? Similarly, if I remove all of the water down here, what happens to the temperature? Water vapor. If I remove all of the water vapor, it gets cold, and the infrared, it has no problem. Now it just leaves. And so the temperature gets cold. See how these things are connected? Okay. If I turn off the X-ray, I guess we'll do that next. Oh, no, I guess we won't do that. Okay, wait. So let me talk first about convection. We've talked about it a lot. Here's the image. I showed it down here. Maybe I should have put these slides in a different direction. It's like boiling water. It's where you have hot below cold. So here it's hot, here it's cold. And that's not the natural order of things. So hot wants to go up and cold wants to go down. Okay. You need to have something that's fluid. So whether that's a liquid or a gas, that's perfectly fine. Just needs to be able to move, right? So for example, if I heat up a pan, that's not going to convect, but the liquid inside will convect, right? Okay. So that's fine. I explained that before. Where on this plot can I get convection? Hold on, sorry, hold on. Can I get convection from 10 to 50? Can I get convection from 50 to 80? Can I get convection only at 50? Or can I not get convection anywhere in the stratosphere? Now, I know you're going to look at this piece and go, there's already convection. That's not what I'm saying. I'm asking for this section, where can I get convection? Oh, that's a weather balloon. Sorry. Yeah, I guess it's not a very good picture. Riley says he might be on board. Relax, relax. Okay, everyone in? Who want to be in? Oh boy. Okay. We have 3 camps. Turn to someone who's not in your camp and convince them that you're right. Click in when you have it. Does that help now? No. What? Heat at the bottom, yeah. Hot, cold. What's that? Yeah, so I'm just thinking here about which sections are hot and which ones are cold in the stratosphere. Not total everywhere. Like, don't look here, don't look here. Ignore those. Just from here to here. This is the stratosphere. So where can convection happen, if at all? Click in if you have it. Okay, I don't know if this is productive. It doesn't look like it's changing very quickly. Okay, so let's think about this. It's hot down here. It's cold up here. This hot air rises, it then cools, and it falls back down. That's convection, right? So just like if we're boiling water, it's hot down here, it makes it all the way to the top, the gas escapes, and then it falls back down again. That's the bubbles, right? Similarly here, it's cold. Cold likes to be at the bottom, so there's no reason for it to go up. It's hot up here, so it's chilling. It's exactly where it wants to be. So no convection happens between 10 to 50. But here it's hot. And so it goes up and it cools, and then it falls again, where it starts heating. So we can have convection between 50 and 80. Good? Yes or no? Yes, okay. All right, last part of the atmosphere. Oh no, second to last part of the atmosphere, thermosphere. So this is the place that's hot. Thermo means hot. And you can see it gets real hot. So this starts at about 80 kilometers and it just starts getting really, really warm. Okay. It's also very, very thin gas, right? So the thickest part of the atmosphere is at the bottom and it gets thinner as you go up. But the temperature is also starting to rise because of the absorption of the X-rays. The X-rays are going in, they're depositing all this energy at the top of the atmosphere. Okay. And then this is the very, very tippy top. This is the exosphere. This is like your, yeah. It goes like this. You can't see what happens in here, but it flattens out. Goes like that, and it flattens through the thermosphere. And then once you get to the exobase, temperature is kind of like a weird definition because that's like saying, like imagine the door is open and no one's pushing on the other side. It's kind of weird to define pressures when you have particles that can leave. So if people are streaming out, I wouldn't define them as being held under pressure. So the very top of the atmosphere, the exosphere, like if you think of exobase, or if you think of exoskeleton, the stuff on the outside, right? This is the layer of the atmosphere that is directly touching space. And these particles here get enough energy and they leave and they never come back. Yeah. Yes, yeah, right here actually. But X-rays get absorbed all through them. So from like 400 all the way down to 80. We just don't show that. It's not interesting. Okay. Very low density. A lot of the X-rays get through, but there is some warmth at the top there. And if you get enough energy, the particles can just leave. Make sense? Okay. I'm going to go back to this a number of times, and you'll see this again at the beginning of the next class. If you can remember the way that this works, X-rays are the most destructive. They strip atom and ion. Then you have ultraviolet radiation. It heats stuff up, right? But it also destroys them as it heats. So for example, ozone here can break apart. Right? We'll use this example as well when we look at a comet because their ultraviolet radiation is breaking apart water molecules. So ices on the surface of the comet get liberated. They're warm, they bounce off, and then they get stripped apart and they form an enormous tail that you'll see. Visible light is almost unimpeded, makes it to the surface, gets absorbed, and re-emitted as infrared light. Everyone's getting this one? Okay. I was gonna do a lecture tutorial, but I think that is gonna make everyone upset. We definitely don't have time. So we're gonna stop. I know, don't get too excited. And then, yeah, Riley says you can go at 7. So if you want to, raise your hand, you would go at 7 if you still have to go to lab before then. Do you see what I'm asking? I've been texting Riley and I asked him if you can leave to get up to the observatory to watch the comet at 7. Like lab itself would not fully be canceled. You don't have lab? So raise your hand if you would go. Okay, I guess I'll stay. Okay, so we'll go to the observatory. It'll just be for y'all. And we'll go look at the comet. And we can talk about some of these processes. Is that fair? Okay, break. Yeah.
That's it.
Today. After this. Today at 7 in 2 hours. Yeah. What? I would be there a little bit before 7, but yeah, you'll be there at 7. So like it's like 7:40, we'll be able to see it.